So thank you all for joining for the second of our workshops this month. My name is Helena. If you went to the Magnets workshop on Tuesday, you will have met me, or possibly one of our other events. If not, hi. Like I say, my name is Helena. I am the Quantum Materials Outreach Officer at the Department of Physics at Oxford. So the name of this workshop is Monopole Hunters. So you might be asking, what is a monopole? What is a magnetic monopole? So the clue is in the name. So mono, meaning one, pole. So we know that magnets have poles, but we know that magnets usually have two poles, right? So again, we have my trusty red and blue bar magnet here that we all know and love. And we've got two ends, so two poles. So we have a north and a south. And we know that all magnets have these two ends, okay? And we know that opposite poles attract and like poles repel. Okay, so how can we get just one pole? Well, that's something that we will be going on a hunt to find throughout this workshop. So first things first, the first thought you might have is, well, what happens if we cut one of these in half? Surely we'd just get, either the red or the blue, one pole or the other. So we're not going to cut one of these in half because cutting through the plastic and everything inside would be a little bit of a pain. But what I do have here is a metal rod, a steel rod that has been magnetized. So that means that it's been turned into a magnet. And I can show you this with the Magneprobe here. So there's a little magnet free to pivot on the end of here, which allows us to explore magnetic fields. And we can see that one end of this rod attracts the blue and the other attracts the red. So we know that this steel rod is acting as a magnet with two poles. So let's try and cut this in half. So that's the same as cutting a magnet in half. So to do this, I'm going to transfer over to share my screen with the visualizer in just a second, but I'm going to just stick it upright in a blob of blue tack to hold it in place. Okay, so let me share my screen. There we go. So now we have our metal rod, move it a little bit further back, held in place with blue tack, and we're going to have a go at cutting this in half. So just to show you again, so we have the top here, which is attracted to the blue part of our Magneprobe. Okay, so let's remember the top part is attracted to the blue. And so I've got here just some snips, and we're going to cut this in half. So let's see if I'm strong enough to do this. It's quite tough, this one. Do it earlier. Yeah. There we go. That went flying a bit. The joys of doing these things live. Okay, so that went behind my screen, the top part, but we still have the bottom part here held with our trusty blue tack. So if we remember, the top part was attracted to the blue part of the magnet. So the bottom part was attracted to the red before. So let's just show that again here. So what do we think? So now we've cut this in half. What do we think, if I move the Magneprobe up to the top, what do we think is going to happen? So the bottom part we know is one pole attracted to the red. If I move the Magneprobe up to the top, it's attracted to the blue again. So we've cut our magnet in half, but we still have two poles. And we can keep doing that. So let me see if I can cut it in half again, or if it's going to be too stiff. Oh, no, I think this one's too thick to do it again. But we've already seen once, if you cut it in half, we still have the two poles. And like I say, we can keep doing that again and again. And actually, if I move that out of the way, if we have a look at our red and blue bar magnet, and we actually take this apart, is this the one? Yeah. So we can take apart our red and blue bar magnet, and inside, we can see what's inside. Inside, we actually have 3 separate magnets. So inside of our single red and blue bar magnet, we have 3 magnets. So put them all together and we have those 2 poles. But if we split that into 3, I can show you that we still have 2 poles. So that's attracted to the blue side of the magnet probe. And here we're attracted to the red. So no matter how many times we split our magnet in half or thirds, we're still going to have 2 poles. So that's not the way that we need to go if we want to get just 1 pole, if we want to get a monopole. Interesting. Okay. So let me stop sharing there. So does that mean that magnetic monopoles don't exist? Well, that's a good question. So the type of monopole that you might be expecting to find if we were, cutting the magnet in half, so that single pole kind of on its own, we haven't found those yet. But we have found something that we call an emergent magnetic monopole. And these are found inside certain materials, inside certain crystals, okay? And they look like a monopole on their own, and they have the same properties, but they're slightly different to what you might think. So it's not like, if you think about electric charge, you have an electron on its own, which is a single point of negative electric charge. So it's not quite the same for a magnetic monopole, but it looks very similar and it has the same properties. So like I say, to find these, we have to look inside a certain type of crystal called spin ice, okay? And spin ice has a certain type of structure that is based around shapes like this. So these are called tetrahedrons, or essentially triangular-based pyramids. And inside this spin ice structure, there's an atom at each of these 4 corners here. And the edges kind of represent the bonds between the atoms, the connections between the atoms. And these tetrahedrons, these triangular pyramids, join together inside the structure at the atoms, at the corners. And they kind of alternate like that in a pattern. So that's the structure of spin ice, okay? And within this spin ice, we can find these emergent magnetic monopoles, okay? So the type of spin ice that we're going to look at is a crystal called Dysprosium Titanate. So that's just a fancy name for a crystal that has 3 different types of atoms. So we've got dysprosium atoms, titanium atoms, and oxygen. Okay, and they're all arranged in this crystal structure with these tetrahedrons, with the atoms at each corner. Okay, and let me show you this on a PowerPoint because it's a little bit tricky to visualize, but hopefully if we break it down into steps, this will help. Okay, so like I say, we have our tetrahedron structure, our pyramid structure, and at each corner, we have an atom. So in this case, we have a dysprosium atom. And these dysprosium atoms, they behave like tiny little magnets. Okay, so if you were at the magnets lecture before, you'll understand that magnets, that atoms can behave like little magnets. And that's all to do with the moving electrons within the atom, generating a tiny, tiny little bit of magnetism. And that's exactly what happens with these dysprosium atoms, okay? And we can represent this bit of magnetism with an arrow, okay? So that's what's shown in this next slide. And we call these little bits of magnetism on each atom a magnetic moment, okay? Or sometimes we call them spin. They're not actually spinning, it's just a name that we use in quantum mechanics, but we call this property spin. And like I say, we represent it with an arrow to kind of show the direction that that magnet is pointing, that that bit of magnetism is pointing. So one direction of the arrow, so with the blue arrows, we could say that the magnet is pointing with the blue end in. And then with the red ones, it will be the red one in. Okay, So the arrows just represent that direction of the spin. And usually within this crystal, each tetrahedron is kind of balanced. Okay, so we'd have 2 arrows pointing inwards and 2 arrows pointing outwards. And so if you averaged that out, the ups would cancel with the downs, so you kind of get no net magnetism there. Okay, and that's repeated throughout the entire 3D structure in something that looks a bit like this. So like I say, it's a little bit tricky to visualize in 3D, but you can see if you follow each of the tetrahedrons, you'll see there's 2 blue arrows, so 2 blue arrows pointing out, and 2 red arrows pointing in as you go from each tetrahedron to the next. So overall, that's balanced. Okay. So we've not found our magnetic monopoles yet. So we're going to look a little bit deeper. Okay. So how do we get those magnetic monopoles? So in order to visualize this, we're going to actually change from looking in 3D to 2D, just to make it a little bit easier. Okay. So what we're going to do is we're going to take those tetrahedron shapes that have 4 atoms, so 4 atoms, 4 corners, and we're going to represent them by squares. Okay, so it's just a visual representation. We're taking these 3D shapes and we're kind of compressing it into 2D. So you can almost imagine we're smushing the pyramid down a bit. So you have a square. So we've got atoms at each corner of the square now. And just like before, we can put our arrows on them. So we can put that there's 2 arrows pointing in and 2 arrows pointing out. So we've got this balanced configuration here. And like before, that's repeated throughout the entire crystal structure. So we have this checkerboard grid. Looks a little bit like a chessboard, okay? And we can put those arrows going all the way across as well. So each of the black squares represents one of these tetrahedrons here, just in 2 dimensions. And remember, at every corner, we have a dysprosium atom. And each black square has 2 arrows going in and 2 arrows going out. So here's where we're going to hunt our monopoles. What happens if we flip one of the arrows? So here. So if you look at the blue square and the orange square, we flipped. So from here, we flipped that green arrow to pointing the other way. So now if you look, the blue square has 3 arrows pointing inwards, so it's not balanced anymore. And if you look at the orange one, we've got the opposite. So we've got 3 arrows pointing outwards, so that's not balanced either. So there we've created, excuse me, in the blue square, we have that unbalanced arrows, so we've made our monopole. We have that single pole, so that single arrow pointing into that square that is acting as a monopole. And so obviously this is a complete structure. The other squares are going to want to try and balance it out, so they're going to try and compensate. So what happens if another square joining the orange one flips? So here we've gone from this configuration to this configuration here. So it flipped another arrow. So now the orange square has moved. So the orange square is in a different place, but it's still got 3 arrows pointing out, and the blue one still has 3 arrows pointing in. And we can keep flipping these arrows. So it's almost like a little puzzle, like you're following the squares. And each time the orange one moves, it's because we've flipped an arrow. And that's the red arrow. Okay, until we get to the end of the structure. And we can still see that the blue square, that has 3 arrows pointing inwards. And the orange square still has 3 arrows pointing outwards. So in each square, we have a monopole. We have a single arrow out of balance with the others. So we have a monopole. And so we've not quite isolated a monopole kind of all by itself. But so the blue square, we've created our sort of north pole, let's say, and it's sufficiently far away from the corresponding south pole in the orange square that if we're measuring the fields, it looks like a monopole. So that's these emergent magnetic monopoles. Okay. And as I showed here, they move throughout this spin ice, throughout this crystal, they move. So if we go back to here, where we just flipped a single arrow, each time we flip an arrow, this orange square moves. So that south pole moves through the crystal. Okay. And this is how we detect them. So as scientists, we can't quite see directly into the crystal in a way that we're kind of visualizing here. So the way that we detect them is we detect when they move. Okay. So as I said before, when we were talking about the atoms, an atom has a tiny bit of magnetism because of the moving electrons. And moving electrons is the same thing as electricity. So electricity produces magnetism. So you might have heard of an electromagnet. So we can create quite strong magnets using electricity. And actually, the opposite is also true. So we can create electricity using magnetism. So if we move a magnet near a wire, it has to be moving, we create electricity. And that's actually how a lot of generators work. That's how we generate quite a lot of our electricity. And because a changing magnetic field, so a moving magnet, creates electricity, as this monopole is moving throughout the crystal, that magnetism is changing, it's moving, so it can actually create a bit of electricity. So what we do to detect it is we wrap a wire around this bit of crystal sample, and we measure the voltage produced in that wire. And each time one of these spins, these arrows, flip, our monopole moves, it changes the magnetic field, and it creates a voltage in that wire. So that's how we detect them. So we don't actually directly detect these emergent monopoles, but we detect them as they move because it induces a voltage in a coil of wire. And this is very, 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 very small changes in magnetism. So we're talking even 1 billion times weaker than the Earth's magnetic field, which is fairly weak. So we need very, very, very delicate, very high sensitivity instruments in order to detect this. So we use something called a squid. So that's an acronym, SQUID, and that stands for a superconducting quantum interference device. So that's a fancy name for what's basically a superconducting coil of wire that can measure these very, very tiny changes in magnetic field because of those very, very tiny bits of voltage that it produces. And that's how we detect these. And what we can actually do is we can detect how fast they're flipping. So every single time one flips, it creates a little bit of voltage. And we can measure how fast those bits of voltage are created. So we've measured that every time it flips, one flips about every millisecond. So we have about 1,000 spins flipping every second. Okay. And like I say, every time one of these flips, it induces a voltage. So we're getting 1,000 tiny little bits of voltage created every second. And what we can actually do is we can turn that into sound. So if you think about it, if your phone is playing some music, what's it doing? Well, it's turning electrical signals into a frequency of vibration, into a sound at a certain pitch. We can do the exact same thing here. So these 1,000 flips per second, that's the same as sound at a frequency of 1 kilohertz. So if you remember, when we're measuring sound frequencies, 1 hertz is 1 per second. So a kilohertz is 1,000 per second, which is exactly how many flips we're getting per second. And we can turn that into sound. So we can actually hear these monopoles moving throughout the crystal. And that's what I've got on this slide here. So hopefully you should be able to hear, when I press play, you should be able to hear the monopoles, the monopole noise. So what you'll hear at first is a low-level background noise, and then you'll be able to hear the change in volume and pitch when we start measuring those monopoles moving. So it should be playing. Let me know if you can't hear it. Let's hear that. We've got our background noise again. Great. So I think that is really cool that we can actually hear these monopoles moving throughout this crystal, even though they're moving so quickly and producing such a tiny little change in magnetic field, we can still hear these monopoles. Okay. Ooh. There we go. Let me stop sharing that now. Okay. So that's our magnetic monopoles. So we found what we call emergent magnetic monopoles in these crystals. Now, they're not magnetic monopoles as you might have predicted by cutting a magnet in half, because we've proved that that doesn't work. But we've managed to find these monopoles if we look in the crystal, where you have those unbalanced spins going into one of these little tetrahedron shapes. And they move throughout the crystal, and we can measure that, and we can hear that. Okay. So, like I say, I think that's pretty awesome. I hope you do too, particularly the sound there. So what we're going to do now is I have a little activity for you all to do. So we're going to hunt some monopoles of our own. So hopefully you should have in your email, you should have received a little activity booklet. So hopefully you have that printed out or viewed on your screen now. If not, I've just put a link in the chat where you can find it. So if we get that open, we can hunt our own monopoles on those 2D grids. So let me share my screen so you can see what I'm talking about here. So here we have the booklet here. It's called Hunt the Monopole. And if we scroll down, we can see we have grids similar to the ones that I showed in the PowerPoint. So if we remember, each black square represents one of these tetrahedrons in the crystal. We just squished it down into 2 dimensions so we can actually visualize it and draw it. And in each of these, we have 2 arrows going in and 2 arrows going out. But we need to hunt the monopoles. So do you remember what I said about the monopoles? We have those unbalanced numbers of arrows going into a square. So we're looking for one black square that has 3 arrows pointing in, and it's going to have a corresponding black square somewhere else in the grid where we have 3 arrows pointing out. So that's what we're hunting for in our monopoles. So get hunting. No spoilers in the chat, because people might work at different paces to you. But by all means, discuss it, say when you found them. It does get progressively harder, okay? So the first one you might find quite quickly, but then by the time you get to the end, so you can see the squares get smaller and smaller, and even smaller as you scroll down. So just to remind you, we're looking for those squares that represent those magnetic monopoles. So we're looking for a black square that has 3 arrows pointing in and a black square that has 3 arrows pointing out. And they're your 2 monopoles. And while we're doing that, I can answer any questions. Okay, so there's a few that I can answer very quickly. So going back to what I was saying about the squid. So that stood for superconducting quantum interference device. Okay. And like I say, they are these superconducting coils of wire that are very, very good at sensing very, very small changes in magnetic field. So if you're interested in learning more about them, they're used in quite a bit of scientific research. So there'll be a lot of information on our websites about those. And if you want to go into even more detail, you can read the papers, the scientific papers that have been written about these very experiments. Okay, so the top voted question is a really good one. So that someone has asked, is this configuration only found in spin ice or any type of magnet? So at the moment, we've only found it in spin ice. So spin ice type structured crystals. But that's a very good question. It might be present in more types of material, but we've only found it in spin ice at the moment. And we've actually only just, so this has been theorized for quite a number of years now, based on what people know about quantum mechanics and how magnets work and how the crystal structure works. But we've only just been able to measure and measure that noise and hear that noise last year. So in 2019, that result came out that we could detect these monopoles moving and actually turn that into sound. So it's still quite a recent discovery that this actually exists, because it's definitely something that you will learn if you go on to study physics or another science that involves magnetism at university. You will learn some fundamental equations, one of which tells you that magnetic monopoles cannot exist. So we've just kind of, in a way, kind of disproved that. But that's kind of how recent this discovery is. So it's still a current area of research. So if we can find another material that has these emergent magnetic monopoles, that would be amazing. But so far, we've only found it in spin ice. So how do you turn something into a magnet? So that's a really good question, because not all materials are magnets themselves. So there's a difference between a material being a magnet and a material being magnetic. So that's quite an important distinction. So for example, we all know this is a magnet, okay? And it can attract other magnets or repel other magnets. But let's say something like a paperclip, we know that's attracted to a magnet, but it itself doesn't act as a magnet. So a paperclip on its own wouldn't be able to pick up other paperclips. So it's magnetic. It's not a magnet, but it's magnetic. Okay, so that's something really important to remember. But you can temporarily turn magnetic materials into magnets. And the way you do this, well, the most common way you can do this is if you get another magnet and you kind of, you have to stroke it along the material repeatedly in the same direction. And that temporarily causes the atoms inside to align like they are in a magnet. And then you could use that paperclip to pick up other paperclips. So that's, I think that I've interpreted right. That's kind of how you turn something into a magnet in an everyday setting. Okay, so we've got some more questions about spin ice. So yeah, I did kind of rush that a bit. So spin ice, it's basically a type of crystal. So when I say crystal, where have I got my little crystal? So I mean, so a crystal is something that looks a bit like this. So I've got an amethyst crystal here. But the word crystal just means something about the structure of the material. Okay, so a crystal means it has a very kind of rigid repeating structure of atoms inside. So a material can look like a crystal, but it's only called a crystal if it has that repeated pattern, that repeated structure of atoms inside. So with the case of spin ice, if you remember, I showed these triangular shaped pyramids with the atoms at the corner. that's that repeating structure inside of spin ice. And that repeats throughout the entire material, the entire crystal. So spin ice is a type of crystal with a certain structure. What is a dysprosium atom? Yes, good question. Let me see if I can find. So whenever you want to know about what a certain type of atom is, the first place I would go to look is the periodic table. So that tells us a lot of things about different atoms. So let me get that up. Let me see if I can find it. So the periodic table, if you're not familiar with it, or if you haven't seen it, you might not have used it much yet. But the periodic table tells you information about every single atom that we have discovered. And it tells you the details about the structure of the atom. So you know that atoms are made up of protons and neutrons in the center, and then you've got electrons surrounding it. So the periodic table tells you how many protons and neutrons are in that element and how many electrons are around the outside of it. And from that information, scientists can kind of infer, we can know what chemical properties it might have. So a dysprosium atom is a reasonably heavy atom by the looks of it. So its chemical symbol is an uppercase D with a lowercase y. So if you look on the periodic table, that's the one you're looking for. And at room temperature, it's a solid. And I can see that its atomic number is 66. So that's a dysprosium atom. But check the periodic table for more information, is what I would say for that. So someone said, can you use any magnet to make something a magnet? So you need a reasonably strong magnet to make a magnetic material also a magnet. It doesn't work with all materials. The material needs to be magnetic itself. And you need to have a reasonably strong magnet. But one thing you can do at school, like I say, with the paperclip or the steel rod that I had, you can make these into magnets. Usually, I think with a bar magnet, just one of these red and blue magnets, if you move it enough times along the material. It might take time, but you can. So another good question here. So when I said that no matter how many times you split a magnet, you still get the two poles. Does this still apply on a subatomic level? So that's a good question. And so magnetism itself is a property that you need to look at the atom as a whole, because it relies on those moving electrons in the atom. So I think it would stop, magnetism itself would stop once you get that to that atomic level. As soon as you go subatomic, I don't think you would have that effect anymore. Like I say, because it relies on the electrons. Yeah, so it's the moving electrons in the atoms that creates the magnetism. So it's only when you look at the atoms as a whole do you see magnetic effects. So I hope that kind of answers it. But certainly, if you keep cutting it down until you maybe got to a single atom, that's probably when it would stop. But even within that atom, you'd still have a north and a south pole within that atom. Like the dysprosium atoms, they acted as a tiny little bar magnet, both with a north and a south pole. Okay. Another good question here, can people be magnetized based on the fact that we are 70% water? And the answer, theoretically, would be yes. So water itself, and if you went to the workshop on Tuesday, I did talk about this there because I think it's a really cool fact. Water is magnetic, but only when it's put inside a really, really strong magnetic field. Okay, so on its own, water isn't magnetic. It's only in the presence of a really strong magnet. But in the presence of a really strong magnet, water is repelled from the magnet. Okay, and that's something that we call diamagnetism. And yes, that is something that happens. And the fact that water molecules react to strong magnetic fields is the reason why we use magnetic resonance imaging, MRI technology in hospitals to image our bodies. So that's a really good question. And if you're interested in that, I would recommend you look up more information. Can electricity be magnetic? So electricity and magnetism are kind of two sides of the same coin. So they'll often be taught as kind of one topic, particularly when you get to university, just as electromagnetism. So electricity produces magnetism, and if you a moving magnet, so it has to be a changing magnetic field. So a moving magnetic field produces electricity. So they kind of go both ways. So electricity produces magnetism, and magnetism kind of produces electricity. Right, so yeah, there's some good questions about how you get the arrows to flip and kind of how you start the monopole process moving. And the answer to that is, as far as I'm aware with current research, it kind of happens on its own because of quantum mechanics. I know that's a very unsatisfying answer, but it's one of those things that there's still research going into, and it's something that it's kind of an intrinsic, it's a property of the material. It's something that happens, and it's predicted through, like I say, through quantum mechanics, through mathematical theory, and we've only just now been able to even detect it properly, because, like I say, because there are so many atoms within that material, and the monopoles move so quickly, it's been really hard to kind of cancel out any background noise and measure these really small changes in magnetic field. But it's something that kind of happens by itself within the material because of quantum mechanics. So if you cut a bar magnet vertically, would it still have both magnetic characteristics? So I imagine you're saying, so instead of cutting it in half like that to try and separate the poles, if you cut it through the middle. And the answer, as far as I'm aware, is yes, you just have two kind of thinner magnets, because you've still got the poles aligning like north-south vertically. You've just kind of cut the magnet, cut the domain kind of in half. So you just have two thinner magnets in that case. But that's a good question. So there's a question here, how do you make the crystal? So I'm not entirely sure how you make this crystal. That's something that you would have to ask one of the scientists who is studying this specific crystal and how to make it. That is one of the branches of science you can go into. You can be a crystal grower and study crystals. There are some people who do that in our group, so they would be the person to ask how exactly they make these crystals. Because it's quite a tricky process, and you can grow crystals so that they have very specific structures and layouts inside. So it's a very tricky subject to do with the level of detail that you might want a crystal to have for a specific experiment. Yeah, so ask a crystallographer. That's the name of that title. Sorry, I don't know the specifics myself. How do you make a magnet? Okay, so I answered that in terms of how do you magnetize materials, but you can make an actual magnet. There's a few different ways. Obviously, there are some rocks in the ground. So there's one, if you were there on Tuesday, you will have known I talked about lodestones and magnetite, which are rocks with iron just naturally occurring in them, which you can dig out the ground, and they're naturally occurring magnets. These type of magnets that we have in here are actually, so they're iron based, but a lot of them are what we call ceramics. So just like your plates at home are ceramic, they're made by kind of putting together the material and firing it in a hot oven, in a very hot oven. So that's one way you can make a magnet. A lot of them are ceramics, so I find that quite interesting. But again, that's another branch of science that you can go into, especially since we're trying to figure out new materials that we can use as magnets, particularly when it comes to superconductors. So that's something that I mentioned. That's a material that can conduct electricity without losing any of the electricity through resistance. And they also have really interesting magnetic effects when they're cooled to really quite low temperatures. And we're researching new ways into how to make those. So again, another current research area. So I think we're probably coming to an end. Yeah, thank you very much for coming and your fantastic questions. And like I say, I hope you enjoyed it and learnt something.